Welcome. I'm David McIntyre. I'm the Director of Product Planning at Samsung. And today I want to share with you compute memory and storage, optimized configurations for a new era of workloads. So the new era of AI and machine learning that we're all involved with has shown a swift increase in demand for memory capacity and performance. The hyper buzzword these days is OpenAI and ChatGPT. And, I did some research looking at this lifearchitect.ai models, and you can see here that the number of modeling parameters is growing astronomically. Billions and billions of parameters are getting created across these different frameworks and models. And it's really astounding how quickly they've grown just over time, driven by these AI and machine learning applications. So that requires a new mind shift in how we look at compute memory and storage resources. So in memory, a while back, there was the storage class memory architectures that were being designed, but now persistence is certainly important for some applications, but we're taking a broader view now on this as with CXL enabling coherency and memory pooling and tiering, we're able to now look at shared resources and semantic memory resources as well. For compute, we're really leaning into how to locally orient compute resources to best support cloud to edge applications. And also UCIe, the chiplets that provide specific functions that can be very tuned for given applications, also a big benefit moving forward. And then for storage, instead of buying a significant storage capacity or renting it and assuming that we have sufficient resources, we now have the opportunity to scale storage and provide tiering even at the storage level and intertwine that with tiering at the memory level to provide a holistic approach to supporting AI and ML and other high growth memory intense applications in memory databases. And another example, so is genomic sequencing. We also need to be cognizant about supporting different data types and also files. So block, file, and object need to be part of our evaluation. So the memory hierarchy that we're all familiar with, the idea there is to keep the hot data close to the CPU and bring it locally to the CPU. Now, the challenges there, as we know, is that the closer that you bring the data with higher performance, it gets more expensive, even though you're basically paying for increased bandwidth. But the capacity and the value of that capacity and price per capacity, I suppose, is at the lower levels of that triangle. But you're also paying for extended latency, not just because of the technologies, but because of the physical distance between the core processors and those media resources. So we have a combination of cold data and hot data types that we need to contend with. So if we look at the disparity of that memory hierarchy on the left versus today's modern workloads, we can see that there's actually an emphasis now on more and more hot data for real-time analytics support, not only ML, but also big data. So we need to step back and see how can we contend with these more aggressive, more complex workloads. So we can do that by creating a new memory hierarchy that's deeper. So it's still based on the baseline hierarchy that we walked through, but we're now also providing a more efficient memory hierarchy to fill the performance gaps and needs. And we can do that with near memory resources such as high bandwidth memory, tapping into CXL with memory expansion, and then also tiering the memory. And then from a storage standpoint, we can deploy massively dense capacity SSD appliance resources, petascale level resources, in fact. So we do have a number of very compelling options that exist today and that we can blend together today for tomorrow's solutions that support these demanding workloads. So data-centric computing. Okay, so we're very familiar with the left diagram where we're basically the traditional compute, memory, and storage architecture that we all know. And the biggest challenge there is scalability, as well as the tax for transferring data back and forth between memory, compute, and storage. And then as we build through on data-centric computing, we're familiar with, on the bottom, in-storage computing, which is computational storage, and Samsung Smart SSD is one production product that is a good example there. And then if we continue this diagram and look at, well, okay, we can now add processing in memory to complement in storage computing. Now we've got some interesting things going on here. For one, we can significantly reduce the data transfers between memory and CPU and storage and CPU. So we're saving power. And we're actually deploying distributed compute resources. And you could even argue a little bit of heterogeneous compute going on here as well, to tune our compute resources to benefit the applications themselves. So the takeaway benefits from this data-centric computing approach: lower power computing, because we're moving the data far less than we were in the more traditional architecture. Data reduction, path reduction. So that's another benefit, because not only are we moving the data less, but we can work on the data where it resides with in-situ processing. And that also frees up those data pipes for the data that still does need to go up to the host, either for functional processing or for a control plane. Now we've freed up that pipeline. So holistically, the overall architecture runs better. So we're not trying to replace the host processor, but we're certainly complementing the host and distributing that host responsibility across different compute nodal points. And then in doing so, we're able to scale our resources to best support the demands of the application, which may be temporal, meaning that for social media applications, there will be some hot times to run those apps where we can add additional resources through a software management layer, both for compute and for storage and memory. So that's a very exciting proposition. Now, there are some challenges that we need to deal with. They're solvable, but we do need to deal with them in data-centric computing. One is the API to the application layer. So there are examples of proprietary API interfaces out there today, and that creates some confusion, especially as we enter into a heterogeneous compute mindset where we want to have the availability of different accelerator resources that best support different application types. So one call to action is to work with our open source communities and standards bodies to develop an API framework that does enable and support heterogeneous compute and also distributed compute. The killer applications, they're looming, they're out there. AI is certainly going to be one of the key drivers. There are others as well. Security is big. It's an underlying requirement across all these fun applications and necessary applications that we talk about. And so by creating POCs and evaluating workloads in these data-centric compute architectures, that's how these killer applications will reside. They're just not going to show up on our doorstep. We have to work hand in hand to make them happen with the highest performance and efficiency. And that the ease of use, I suppose, is a combination of both the open source outreach to our application developers that are developing those killer applications and providing them the easiest methodology to tap into data-centric computing through simple calls where they do not have to become FPGA specialists in programming or any other accelerator specialist, that they can have simple software level calls without disrupting their software ecosystem that enables them to take advantage of these benefits. And then jumping to CXL, so we have, of course, we know about the three device types. SmartNICs, very good with type 1, type 2 on accelerators with memory, and type 3 with memory buffers. And then CXL 2.0, this is the version that provides us with that resource pooling and disaggregation benefit. And then CXL 3.0 provides the opportunity of supporting this heterogeneous compute that we've been talking through this presentation about. And so having that CXL switch now allows us now to access memory pooling and memory tiering across multiple accelerator types. And that's really exciting. So from Samsung's perspective, if we focus on the type 2 and type 3 devices across accelerators, memory buffers, we are looking at proposing these sorts of topologies. So for memory expander, which is a CXL type 3 device, we can provide high bandwidth, low latency without a long tail and use the CXL.mem protocol. For the middle category of device, a tiered memory solution, which is very important for some of these higher performance applications. We would also utilize the .mem and .io CXL protocol functions and provide an active data path as well through .io. And then for the last category, the accelerators themselves, this would be a hybrid type 2, type 3 device, an accelerator with a CXL interface. So we would have all three functions supported: .cache, .mem, .io, CXL interface, the accelerator with in-house memory, perhaps tiered memory or even pooled memory available to provide the best performance for the applications. So instead of balancing, now we can look at blending these application-driven resources using the CXL foundation to do so. So this is really exciting. So in summary, CXL is the enabling foundation for application-oriented memory topologies. It supports data-centric computing and moreover supports heterogeneous compute by providing the necessary memory resources to make heterogeneous compute effective. Some of the challenges to exploit these CXL-based architectures include addressing the CXL latencies by understanding them from the application development layer, and just appreciating that some DRAM types have to require lower latency, and that CXL may have some extended latencies to it, but can be balanced out because of the inherent benefits of expansion, pooling, and tiering of those memory resources through CXL. I've talked about open source accelerator programming frameworks. That's a call to action for us in the industry to really embrace this approach versus proprietary programming stacks. And then for data-centric and heterogeneous computing adoption, the best way to do that from our end customers is to work with them in workload validation and support. So my real call to action here is to support the end market and those key customers that make up these markets in AI, in-memory database, and genomics, and many other markets that have the potential to be that killer application that we're all pursuing. By becoming one with our application developer, understanding their requirements, and in product development and product planning, work hand in hand to come up with solutions that best support these very exciting applications. So thank you for your time.